following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
All right. The quiz on Thursday will cover up through piezoelectricity. You've had a set of notes in your hands that cover just about everything that I wanted to say about piezoelectricity. There are other moduli that one could talk about, but these follow quite directly from the one or two that we will do. So we will not have anything to say about elasticity until the last lecture of the term, which is a nice outcome because you certainly don't want to take a quiz on fourth-rank tensors. You'll spend the entire hour just writing out all these cumbersome equations. All right, so the quiz will cover up through piezoelectricity, including a few of the representation surfaces that we'll examine today. The thing that we'll be looking at is, yeah, I'm sorry, you had a question?
Yes, a question. Well, you said where it would end, but where does it begin, for example?
All of third rank tensors.
Okay.
So we had just a little bit of that going into the second quiz.
Okay.
And we didn't really ask anything about that on the second quiz. Okay. So it'd be third-rank tensors, but you have to use second-rank tensors to define third-rank tensors. So it really will be not the emphasis, but certainly you should be familiar with the early part of what we did with second-rank tensors. All right, so today we'll look at some representation surfaces to your wonder and delight at how incredibly anisotropic the variation of these third-rank properties are with direction. One of the things that I love to do for problems when we get to these different piezoelectric effects is make up hypothetical devices just for fun. So among those that I've invented, the first one is a earthquake sensing device, because it's well known that California is going to split in half and half will fall into the sea any day now. So if this is the San Andreas Fault, I have developed large prismatic monoclinic crystals that I embed into the San Andreas Fault at regular intervals. The bottom of these crystals is grounded. There's an electrode at the top. And if the San Andreas Fault starts to move and there is shear on these crystals, there will be a charge developed on the top. And I ask you to relate the charge on the top in terms of the piezoelectric moduli to the shear along the San Andreas Fault. So there's a very clever little device that clearly is going to be lucrative because these crystals will have to be huge in size and they'll cost more even than silicon. Another device that I've invented is used down on the Boston Fish Pier. This is a crystal on which I hang a pan, and you put fish in it. That creates a tensile stress in this direction. We measure the charge on this face, and we put a little meter that measures the charge that's accumulated. So this is how the fishermen can weigh their fish after they haul them in off the boat. So you see, this is really practical material we're dealing with. This has applications in all realms of life. So today I'd like to show you also another problem that sets this up, and I pass this out just so you can again have a look at some of the questions that you should be equipped to answer. So here, not fully expecting anybody to do it, but you can see the sorts of problems one might ask. Here is problem set number 16, which asks you, should you be so inclined to think about manipulations of third-rank tensors. But then the second question is an idea for a device which the Center for Material Science and Engineering is considering employing here in Building 13, and you can read all about that. This is the famous soup cell. I think probably you will see some sort of, for fun, modulus for a particular device on the quiz. I haven't made one up yet, but I think you'll have a look at something like that. And when we do the longitudinal piezoelectric modulus for quartz, which we'll do momentarily, this will give you an idea of how to set up these expressions. The problem basically is that the direct piezoelectric effect measures a polarization in terms of all of the elements of applied stress. So there is a modulus dij times all of the elements of stress sigma jk. So this, until you use the condensation of subscripts, contains 9 terms going this way and 3 equations going this way. As we discussed earlier, since only 6 of the 9 elements of stress are independent, you can condense this down into a 3 by 6 array of terms. The problem in doing that, though, even though one has only 18 different moduli to work with instead of 27, that's a considerable economy in notation and an elimination of a great deal of redundancy. The matrix form of this relation, and I emphasize that it is a matrix and it's no longer a tensor, the matrix form cannot be transformed. Again, there are only 6 terms in the matrix elements of stress, and there are 3 equations, again, one for each component of polarization. So instead of having 27, one has only 18. But if you are considering changing the reference axes, and that is one of the things that it's interesting to do for these various moduli that one can define, change the orientation of a particular rod-shaped specimen that you cut out of a crystal to different crystallographic orientations, and then ask how the scalar modulus changes as you change the direction in which you've sliced out the wafer or the rod of material. In order to do that, you want to transform the basic piezoelectric tensor to a new set of reference axes. And you cannot transform the dij's because they are a matrix and not a tensor, and no law of transformation is defined. So what you have to do in any generic problem of this sort is, for a particular single crystal, look up the form of the dij matrix that will have the equalities between tensor elements written in, and the zeros, those moduli which are identically 0, entered into the array. And then you have to work your way backwards to get to the full tensor notation. So we'll see this when we look at the moduli for Symmetry 3.2. You'll have to write in the exact matrix subscripts without absorbing the equalities in the notation. And then you'll have to expand the matrix terms into full 3 subscript tensor terms. And then if you want to transform the axes, which is to say you want to cut out your specimen, be it a plate or a rod, in a different orientation, you have to transform the full 3 subscript tensor elements to a new setting. And then if you want to continue to work in that setting in the compact matrix form, collapse it back down to matrix form, insert the equalities, and then you're back to where you started from. So this problem of seeing how moduli that describe different specimens, different phenomena, vary with crystal symmetry, you have to go through this problem of expanding the compact form and then collapsing back down when you've got it as a function of some orientational angle or in terms of a coordinate system that you want to work in. The problem is exactly the same for elasticity, and we'll look at some of these moduli next term. You've heard these names before, I'm sure, Young's modulus, shear modulus, and so on. We'll take a look on next Tuesday, a week from today, at Young's modulus, which is one of the more important ones. And probably you're used to seeing this in the form of information for a polycrystalline material, which is essentially isotropic. The modulus is much more interesting for single crystal materials. And then the surfaces that are defined, particularly for the lower symmetries, are absolutely wild things with lumps and wiggles and lobes and things of that sort. Nothing like the dumb old uninteresting ellipsoids that we encountered for second rank properties. Okay, so let's then take a look at how we had set up and defined the direct piezoelectric effect. We set this up as a proper tensor relation, saying that P1 is equal to D1. And then you'll recall we have 9 elements of strain: sigma 1,1, sigma 1,2, sigma 1,3, sigma 2,1, sigma 2,2, sigma 2,3, sigma 3,1, sigma 3,2, and sigma 3,3. But the tensor is symmetric, so we really only need to enter into our relation 6 of these 9 terms explicitly. And what we did was to replace the 2 subscripts on the elements of strain, which again you need if you want to refer those elements of those elements of stress to a different coordinate system. You have to know the elements of stress in tensor form. But we converted to 6 terms by going and replacing the pairs of subscripts with a single 1, 2, and 3, marching down the diagonal of the tensor this way, and then marching up the right-hand side, calling 2, 3, 4, and calling 1, 3, 5, and finally ending up in this slot here, and we called that 6. So that was the notation we used to get to a matrix representation, but the place where all this started is, and I'll write just one line of this to be merciful, D1, 1, 1 times sigma 1, 1. So this pair of subscripts goes with this pair, plus D1, 2, 2. I'm putting that one in next because we're going to number the terms for stress in this order, 1 through 6, times sigma 2, 2, plus D1, 3, 3, times sigma 3, 3, plus D1, 2, 3, times sigma 2, 3, plus D1, 3, 2, times sigma 3, 2, plus D1, 1, I'm sorry, D1, number 4 is 2, 3, times sigma 2, 3, times plus D1, 3, 2, times sigma 3, 2. And finally, we end up in slot number 6, and we have a D1, 1, 2, times sigma 1, 2, plus a D1, 2, 1, times sigma 2, 1. Look at that. There's an equation that covers 2 whole blackboards. So if we now condense this down to matrix form, we would say that P1 is D11 times sigma 1 plus D12 times sigma 2 plus D13 times sigma 3 plus, and now we have this messy problem with the 2's. We have a D14 times sigma 4 plus, again, a D14 times a sigma, and 2, 3 is equal to C through 3, 2, so I can call this 4. And then these terms become 1, 5, sigma 5, and again a 1, 5 times sigma 5, plus a 1, 6 times sigma 6, plus D1, 6 times sigma 6. Okay, now we have to make a choice. Either we are going to have, in a general matrix relation, that P sub I is equal to dij times sigma j, if j is equal to 1, 2, or 3, but it's equal to 2 dij times sigma j if j is equal to 4, 5, or 6. And that is something we like to avoid if possible. That's ugly. That's ugly. And it's going to be a hell of a matrix if we have factors of 2 in front of some of the matrix elements, but not in terms of others. So this is something we could do. Hey, it's our ball game, we make up the rules, but that's going to be an ugly thing to have to deal with. So instead, as we mentioned last time, what we will do is to lump together these terms and define D14, not as these individual tensor elements, but define those matrix elements as the sum of these two elements. And then we saw before that, saw last time in our earlier meeting, that from the converse piezoelectric effect, which expresses strain in terms of an applied field, where the elements of strain 1, 2, 3, and 3, 2 appear in separate equations, and knowing that the same array of piezoelectric coefficients amazingly describes the converse piezoelectric effect as well as the direct piezoelectric effect, we know that D123 equals D132, and that is from the converse effect. So equivalent to saying this is to define D14 as twice D123, because these two elements are equal. So we're eating the factor of 2 here so that we can write a nice matrix relation that doesn't involve a factor of 2. So this, making this combination of terms for the shear stresses, we would have simply D14 sigma 4 plus D15 times sigma 5 plus D16 times sigma 6. And we can say in general, for the other two equations, by analogy to this one, that P sub I is Dij times sigma j. A nice, neat matrix relation, but one for which, unfortunately, there is no law of transformation for the matrix moduli Dij. If we want to change to another coordinate system, we have to be prepared to resurrect this full 3 subscript notation on the piezoelectric moduli. Okay, comments or questions at this point? All right, if not, let me remind you that in the notes which I distributed last time, there are summarized all of the constraints imposed on the piezoelectric moduli for single crystals. And again, these constraints, these requirements that the tensors remain invariant for the change of axes produced by a symmetry element that the crystal possesses. These transformations show that no third-rank tensor property can exist in a crystal that has inversion. So the 11 Laue groups, so-called, that possess inversion have absolutely no property and can be not considered further for third-rank properties. And then one must consider all of the 32 minus 11, 21 point groups that lack inversion separately. There's no reason why they should behave the same way. You remember that for second-rank tensor properties, we pulled the argument that inversion imposes no restrictions or constraints whatsoever on second-rank properties, so therefore two different symmetries that differed only by the presence or absence of an inversion center. That is to say, you change two to 2 over m if you add inversion, but the argument was inversion requires nothing, so the constraints for symmetry 2 look exactly like those for symmetry m. Here, you've got to plod through every single one of the non-centrosymmetric point groups separately, and they all have tensors that have different forms. So what I'd like to do is look at one specific one, and that is the matrix for symmetry 3-2. That is a point group that you recall has a 3-fold axis and 2-fold axes at intervals of 60 degrees. And in your list of equalities and absences, 3-2, where the 3 is parallel to the axis x3, and the 2-fold axis is parallel to x1. So we're defining this as x1, this as x3, and x2 comes out halfway between the two. So let me draw this looking down along the 3-fold axis. These are all 2-fold axes. And we'll take x1 in this direction. x2 pokes out in between 2-fold axes, two 2-fold axes, and x3 comes straight up along the 3-fold axis. With that coordinate system, the form of the piezoelectric modulus matrix has this form: d11 minus d11, 0, d14, 0, 0, 0, 0, 0, d15 minus d14, 0, and in the bottom row, d31, d31, d33, 0, 0, 0. So this matrix with the equalities put in is obtained by looking at the full 3-subscript tensor and requiring that it look the same before and after any of the rotations involved by these 3 distinct axes, the 3-fold and the pair of 2-folds. Okay, now there are many different scalar moduli that one could define, some of them serious and worth the consideration because of the application in devices or other practical situations. The modulus that I'd like to examine is something called the longitudinal piezoelectric effect. And let's emphasize again that it is impossible to come up with one representation surface that fits every need. Because, again, the direct piezoelectric effect relates the components of a vector to a tensor, sigma ij. There are 6 independent tensor elements. So how can you describe how this vector is going to change as you change orientation of a crystal whose behavior is described by all of these moduli? But I would point out, however, that there are only 2 distinct. Whoops, I'm sorry. This is D14. I don't know how I made that D15. There are only, in this array, and I slipped a notch, excuse me. Last couple of days are such that I am not able to even read from my notes. So these bottom lines, my apologies, are all 0. And there are 2 moduli, D11 and D14. So they're 2 independent numbers, but they appear as different matrix elements and therefore different tensor elements as well. And this should be minus 2d14. I'm sorry, I slipped down a notch and I got some for 3, 2 and some for 6. And I'm glad I found it at this point, or I'd really be in deep trouble. Okay, so two numbers, and that is, in fact, the form of the matrix for symmetry 3-2. So the longitudinal piezoelectric effect is one of the representation surfaces that gives you the way in which the polarization will change for one very, very specific type of stress. In particular, what we'll do is set this up as a coordinate system, and we will look at a coordinate system where this is the reference axis x1. We'll come down with a compressive stress sigma 1,1 along that axis, and therefore we're applying a uniaxial stress which has just one component of stress. So that's very specialized. In general, there would be 6 different components of stress, but we're looking at one specific stimulus applied to this crystal plate. In response to that sigma 1,1, there are charges induced on all of these surfaces. And these charges, this charge per unit area, is proportional to the polarization, component of polarization P1, the component of polarization P2, along the surface out of which x2 comes, and the charge per unit area, or the polarization along x3. So this would be P3, and this would be the direction of x3. Now, I deliberately tried to show this sample as a thin wafer, which has a much larger surface area here than it does on the other two surfaces, a much smaller area there. Therefore, since polarization is charge per unit area, if this area normal to x1 is a very large area, there's a lot of charge accumulated there, and it's going to be easy to measure. If we make the wafer vanishingly thin, then the charge per unit area is high, but the total area is small, so there's going to be a negligible accumulation of charge on these two side surfaces. So the longitudinal piezoelectric effect and the longitudinal piezoelectric modulus is an effect where we look at the component of polarization P1 in response to an applied stress sigma 1,1. Okay, so it's that simple. Look at all the terms we've thrown out. We've thrown out a whole bunch of elements of stress, which we could impose if we wanted to, and we've thrown away 2 of the 3 components of polarization by designing a specialized sample. So all that's left then is that P1 equals sigma 1,1, and the relation between those 2 parameters is D111. Okay, so all this is going to hinge on one single piezoelectric modulus, D111, and how that changes with direction. So this is for one orientation of a plate. And I have not specified how the orientation of this plate is related to the symmetry axes. So let's do that now. What I'm going to assume is that this is a crystal. Doesn't look like it's hexagonal, but imagine that this is a crystal of quartz. And we could look at an x1 that's in this direction, and imagine that we have cut out of this crystal a wafer that has a normal along x1, and then relative to this coordinate system, if this is x1, the modulus D111 would tell us what charge is accumulated on these 2 surfaces. But now what we could do, if we wanted to know how this modulus changed with direction, would be to cut out a plate, a thin plate, in another orientation, where this is x1 prime, and this has changed relative to the orientation of the cell edges in the crystal is fixed. We're just cutting a wafer out in a different orientation. So this is x1 prime. We're going to, again, squeeze it with a tensile stress sigma 1,1 prime. And we'll ask how the polarization P1 prime is related to sigma 1,1 prime. And the answer is that P1 prime will be a tensor element D11 prime times sigma 1,1 prime. Okay. So what we are asking essentially is how does D11 transform when we take the direction of x1 in a different orientation and thus change the value of D11 prime. It's going to change all of the piezoelectric matrix elements, but we're looking at an effect in a sample that is deliberately prepared such that we will measure only the surface charge given by P1 prime, and therefore the way in which the properties of this plate change as we vary the way in which we've sliced it out of the single crystal is going to be simply the variation of D11 prime with direction. Okay? So this is the general nature of what we will do when we define any of the scalar moduli related to the piezoelectric modulus tensor. Okay, we can change our notation a little bit in that we have a modulus, which I'll define as a scalar modulus D, and that D is going to be D111 prime. And I know how to evaluate that. D11 prime will be C1L, C1M, C1N, where these are direction cosines, times all of the elements in the original tensors, D, L, M, N, and the tensor referred to the original coordinate system. So even though this looks simple, it's just one modulus, when we transform it, we've got a product of 3 direction cosines out in front of every single one of the 27 tensor elements in the original tensor. Okay, so it's not as trivial as it seems. So this is how this modulus that relates compressive stress to induced surface charge will change with orientation. But what are these direction cosines? These are the direction cosines, not the full direction cosine matrix. These are the direction cosines for x1 prime. Okay? So we can get rid of these two subscript notation if it's understood that these are the direction cosines of x1 and simply call these L1, LL, LM, and Ln, just as we did for the direction cosines of a vector, because we're only concerned about the orientation of one of the axes, namely x1 prime. We don't care diddly bop about x2 prime or x3 prime, because these don't enter into the modulus that we have defined. And this will be times dLmn. Okay, so what we're doing clear? So we have defined this particular effect in terms of those of the 27 piezoelectric moduli which are necessary to describe it. And then we've established how that they will change with a change of the direction of one particular direction, and we don't care anything about x2 or x3. All right, now we go through this process of inserting, for matrix notation with the equalities built in, the proper matrix notation. And the first term is D11 in matrix notation. That's this term up here in the upper left-hand corner. The second term, the term that we've written as minus D11, that's not D11 at all. This is, by definition, D12. And we need the true subscripts if we're going to transform this. So this really is not even a matrix because the subscripts have lost meaning and we're just using them to identify equalities. Then comes a 0, and next comes something that we've labeled D14, and the subscripts there are correct. That is indeed the fourth term in the first row. But we're going to want to convert D14 into a tensor element momentarily. But let's get the rest of the terms that are non-zero. This is really D25. So the next term that is non-zero is D25, which just happens, because of symmetry, to be equal to minus D14. But this is the true matrix subscripts, and this is the true matrix subscript here. The next term over to the right is the fifth and final non-zero term. This is minus 2D11, and this is really D26. Those are the true matrix elements. So we put in the proper matrix subscripts. And now the next final step in the expansion is to convert these terms into actual tensor elements. So this is D111. And these are tensor subscripts, so this is something we can transform. This is D12. In tensor notation, this is D122. And that's something that has a law of transformation. D14 is really D123 plus D132. We lump two tensor elements together to define this modulus. D minus D14 that appears in the next to the last non-zero slot is D25. D25 is really D231 plus D213. Then finally, D26 is D121. Oops, D121, that's right, plus D112. I'm sorry, D26, you're right. That's down in the second row. D221 and D212. Now we've got something we can transform. The law for transformation is L sub L, L sub M, L sub N, D L M N. And these are the direction cosines of x1. So this term will transform as L1, L1, L1 times D111. The next term will transform as D L1, L2, L2 times D122, and that will be D122 prime for a different orientation of x1. This will be two terms. This will be L123, and I can write them in any order. So this is L123 times D123 plus D132. And these terms prime, when we change axes, are going to be equal to D2, L2, L1, L3 times D231 plus D213. And this last term will be L1, L2 squared times D221 plus D212. All right, so this now is our new tensor element D11 prime. And that's given by this sum of terms. So we'll have a first term L1 cubed times D111. If I look through these other terms, that's the only term in L1 cubed that I'll have. The next term will involve the product of three cosines L1 and L2 squared times D122. And if I go down here, here's an L1, L2 squared again. So I have plus D221 plus D212. And then finally, the other coefficient that I have is plus L1, L1, L2, L3, which is what this should be. And that will be times the sum of terms D123 plus D132. I've here got the same thing again, plus D231 plus D213. And I have a total of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 terms. Okay, that is how the longitudinal piezoelectric modulus will change as we change the direction of the normal to the plate that we have cut out of the crystal. So these are direction cosines relative to the crystallographic axes. L3 is the angle between the normal to the plate and the threefold axis. L1 is the angle, cosine of the angle between the normal to the plate and one of the twofold axes, and L2 is the direction cosine for the normal to the threefold axis and the twofold axis. Okay, so we've got it now in terms of tensor elements. And now, yeah?
Is it at all reasonable to assume instead of taking those sums like D123, D132, just saying 2D123, is that okay to assume? Or not necessarily?
No, we could do that, but I did it the long way to not obscure what we're doing, okay? This is a well-defined summation over subscripts, and we're going to collapse immediately down to the sums, and we're going to replace the equalities. So let's see what comes out of this if we now, having reached the zenith, having transformed the tensor elements, go down and replace this with a consolidation of terms and an insertion of the equalities between the matrix elements. Okay, the first term is D11. So I will have L1 cubed times D11. And notice I'm getting third powers of direction cosines, which is going to be what causes the exotic nature of these anisotropies. And then I have a product of L1 and L2 squared. And this is D12. And this second term is, where did it go? This is D21 plus D212. And that is what we called D26. And then finally, this product of three different direction cosines, L1, L2, L3. And we have D231 plus D213, and this is D25. And again, an L1, L2, L3 times D14. And the second term here is D25. I've done it correctly. D25. This is D24. And this one is D24. Okay, let's now insert the equalities back to where we came from. D11 is D11. D12, however, for symmetry 3-2, going to my handy dandy chart of symmetry restrictions. I don't want to do that. That's 4th rank. Still on the board? Yes, thank you. When your nose is in it, it's hard to see. Okay, D12 is minus D11, and D26 is minus 2D11. So these two terms can be consolidated, L1 cubed plus L1 L2 squared times D11 minus D11. So these two terms die, and I have a minus 2 D11 that's left. If I insert the equalities here, I'll have L1, L2, L3. D25 is minus D14. And here's a D14 itself, so these two terms die. And then I have D25, and that is, I don't have D25. Where did I get the extra one? Okay. I'll take your word for it. And I know how it has to turn out. Okay, so these two terms kill each other. And I'm left with then an L1, L2, L3. Or have I left something out? This is D1. This is D1, 5, and D2, 3, 1, and D2, 3. This is D2, and the combination of 1, 3, and 3, 1 is D2, 5, right? And if I look at my equalities, this is L1, L2, L3, minus D14 plus D14 plus D25, and D25 is minus D14. Let me check my notes and see what I've got here. Okay, D25 is minus D14, and then I have just a D14. I don't know. I see what I did. I put it in the wrong slot. This is D14, and D25 is the one that's minus D14. So this term dies, which is nice because that cross term is messy. So what I'm left with then, if I check against my notes, is L1 cubed plus L1 L2 squared times D11, and then I have minus D1 minus, and this doesn't belong in here. It's just, this is this wants to end up being L1 cubed minus 3 L1 L2 squared times D11. Okay, the first term is L1 cubed, that's correct. The second term is L1 L2 squared. We've got a minus D1 plus minus 2 D11. So I have minus 3. This should be a minus. Yeah, that carries down to a minus. So I have minus 3 L1 L2 squared, all time D11. Okay, so what we have ended up with is an expression for the longitudinal piezoelectric modulus as a function of orientation. The surprising thing is that L3 does not appear here at all. It doesn't depend on the angle between the normal to the plate and the threefold axis. Depends only on one modulus, and that is a remarkable thing. This says that the shape of this surface is independent essentially of the property, any property that relates D11 prime to a uniaxial stimulus, sigma 11, and you measure a vector component in the same direction, is always going to have this universal surface. And it involves just a geometric term and then one modulus that changes the magnitude of the longitudinal piezoelectric modulus but does not change the asymmetry. So let's see what this function looks like as a function of direction. Maybe we better wait for that till we come back, because that's going to take a few minutes. So this is what we found. That is correct. And we have to now decide what this looks like, which will take a few more minutes, but let's stop here rather than run late. All right, let's take our 10-minute break as usual.